Okay, welcome to Tor Vergata and to our workshop on topology of data. So it's very exciting for me because this is the first time that I organize a workshop here after many years, so it's really great. The department is interested in applied topology. We recently hired Sarah, who is organizing with me this workshop, and I have to thank the organization, so the administration of the university. They did a great job, they helped us a lot. I have to thank the Excellence Project coordinator, Domenico Marinucci, who was supportive. In fact, the workshop is funded by this Excellence grant of the university. So, yes. It's a pleasure, and thanks for coming, and enjoy.
So, here we are at our first talk. It's a very great pleasure for me to have Bastian Rieck here to present his work. I'm very happy and very excited of listening to this work because it's perfectly fitting in the spirit of the event. So in the combination between topological tools and machine learning stuff. Bastian Rieck is now principal investigator at the IDOS lab in Munich. His work comes and the origin from the visual information, and then he moved towards machine learning, always with the topology and geometry behind, I think. So the stage is yours, and we will listen. Thank you.
Thank you very much. It's great to be here and see so many people in person that I only ever recognized like this with a window for their name under them. So I might blank on some of the names later on, but luckily we have our name tags here. So of course, in the spirit of post-pandemic talks, I have to ask, can you see my slides? No, but okay, seriously, it's great to be here, and looking forward to discussing with you later. So I'm going to talk about geometrical and topological loss terms for shape analysis, and I'm also trying to give, alongside that, I'm going to try to give you a brief introduction into some machine learning techniques, but again, a little bit cursory and expository, so you'll have to see how this goes. I, of course, have to start with a nice quote from Gunnar Carlsson, or at least paraphrase from him. So shape analysis, at least for me, is crucial, not only for biomedical applications, but given my background now and my position, I find myself easily motivated by biomedical applications because it's one way for me as a mathematician to basically say, hey, I'm doing something very, very good for other people, or maybe improve the lives of some patients, at least 10 years down the road, if all of these things work out. I want to say that shapes definitely occur in other applications as well, so this is not an exclusion thing, it's more like one thing that where I can really understand what is going on. And yeah, to paraphrase Gunnar Carlsson, data has shape, right? Shape has meaning, and meaning, hopefully, drives understanding of complex phenomena. And of course, we know how to do shape analysis for meshes, because then everything is easy. We have this beautiful statue, Winged Liberty. I always love to use that. And if we zoom in a little bit, we can see that, okay, this is a triangular mesh, and we know how to deal with these things. There are great algorithms from differential geometry, for instance, differential discrete geometry, I should maybe say, where you can analyze things like a discrete curvature and these sort of things. But reality, of course, is often messy, and we are dealing with point clouds. So we get something like this on the left-hand side from our data collection procedure, and what we want to have, or what we want to see, is this platonic ideal of a point cloud. And now, of course, you know how this works, but I think it's good to set the stage a little bit. We can calculate things like a Vietoris-Rips complex, so the complex that you get if you look at all the pairwise intersections of subsets that have pairwise distances less than or equal to epsilon. We can grow the Euclidean balls around this. It always looks a little bit like grapes to me if I change the colors nicely. So this is really great. We know what to do with this. We can even go further and get persistent homology from these approaches, so we can calculate the Vietoris-Rips complex for every value of epsilon, and we watch how the topological features change. We assign each feature duration, we know when it was created, when it was destroyed in the persistence diagram, and then we can obtain these nice diagrams from our point cloud. So far so good. You don't need me to tell you the details about these calculations. There's wonderful math behind that in terms of modules, for instance, or in terms of matrix reductions. There's people in the room that are working on accelerating this, making this super fast. There's people in the room like myself who are just happy that those people exist and then try to plug it into an algorithm and make it work. We also know that there are distances between those diagrams, and again, just as a refresher, these are the ones that I personally like. Doesn't mean that there aren't others, right? The first one you might encounter is, of course, the bottleneck distance. So you do the optimal transport or optimal matching calculation. You look at the infimum of all these matchings. And then, of course, you can generalize this a little bit to the Wasserstein distance. So far, so good. These distances are nice, I would say, because if we think about the implementation for a second there, all of this is optimal transport on point clouds, essentially, or on 2D point clouds. And optimal transport has recently also undergone a real revolution in terms of algorithms. So there's work by Marco Couturi and colleagues, for instance, on entropic regularization for optimal transport. And so we have massively parallelizable and really well-written algorithms that permit us to do these types of matching problems. We also have stability theorems, and I like this example because it also illustrates a kind of misunderstanding. And I think Pavel has a great paper with now I'm blanking on the name, Catherine Turner, hopefully, I'm not sure. Yeah, on this, where they do away with some of the misconceptions of stability theorems. And I really, really like this because stability is often, when you read people coming in from the outside, they often misunderstand the stability theorem as saying, yeah, it's stable against all types of noise. And then it's not entirely true. It is stable against this small type of noise, right? So if we have a cycle here, this works. If we have a little bit of a different cycle here, this also works. But if we add bad outliers here inside, then suddenly our persistence diagram changes quite a lot. So just as a reminder for this, because that can sometimes be critical, if this is the noise that you get in your applications, then boy, oh boy, you have to change your filtration here, potentially pick a distance to measure filtration or do some other kinds of things to mitigate this. Now, this brings me to the, let's say, I would say it's the hopefully the classical new pipeline for topological machine learning. So you take a point cloud, you do persistent homology, and I like this image because it's always like a little bit like a coffee grinder, because it refines things and makes them palatable for other tasks. Like a coffee grinder, you get the persistence diagrams out of there, and then you can do some machine learning. And it is this type of arrow, this last one, that I want to focus on and then zoom into a little bit, because, and I don't know if you had the chance to listen to an interview by Frédéric Chazal yesterday in the AATIN interview series. If you don't, okay, sorry, I need to do the advertising here as a co-director of AATIN, so please sign up to AATIN. It's free, and you get access to these cool things, and we really try to make content accessible to more people. And also, from my point of view, if you have feedback for us as co-directors, as people doing this, please let us know what we can do better. Please let us know things that you miss, or where you're saying like, hey, these people should also be invited for talks, or you're missing some good resources here. We're really, really open to these sort of suggestions. Coming back to this arrow now. Fred said something very great yesterday that resonated very well and set a good stage for this talk, namely, prior to, let's say, the machine learning revolution of the last few years, where these algorithms got more and more accessible, people have been using topological features more as like a static one-time thing. So they had the data, they extracted some features, and then they tried to make sense of the features that they had or analyze something like this. This is not wrong, and it's also a very good thing to do. In particular, if you have a low sample regime, or if you're looking for hypotheses that you want to generate about your data. Nevertheless, if we now have this type of pipeline here with recent additions to some neural network architectures, we can actually make persistent homology or topological features in general, to a certain extent, differentiable and depend on tasks. And here's a little bit of a selection of works where this has been tried out. There's a work by Poulenard and colleagues on topological function optimization. There's work by Michael Moore and colleagues on topological autoencoders, which is what we'll be discussing next. And of course, there's work by Carrière and colleagues on optimizing persistent homology-based functions. In particular, the latter one is super great if you want to read like a very succinct and very concise summary of what is doable at the moment, because they also derive kind of the theoretical conditions for making optimization work in this space. Now, brief introduction to some machine learning techniques for representation learning. Sorry for the long title, but I want to make it clear that this is just a very, very small facet here. And we're going to start with something that has nothing to do with topology, but that is a core concept in recent representation learning approaches. So in representation learning, the idea is that you have some data and you want to learn a representation that is useful for certain tasks. The task can be visualization, the task can be something else, the task can even be interpolation between your data points and so on. But in general, you always have one architecture that will crop up time and time again, and this is the simplest instance of that, namely the autoencoder. The autoencoder is a neural network that has an input data x, an output data x tilde, and a latent representation z. And the funny thing is that typically your input data lives in a big D-dimensional space, and your reconstructed data also lives in a big D-dimensional space, and your latent representation lives in a small D-dimensional space. And typically what you want to have is the input data is much, much higher dimensional than the output data. And you use a loss function, L script, between x and x tilde to measure the quality of the reconstruction. And don't lose your microphone. Oh, this is okay, I can do this. So what we have here is an encoder-decoder architecture, essentially. I'm gonna wait for a second.
High technology.
Oh, well, if it works, right? Okay, thank you. Let's hope that this. Sorry. Yeah, that's.
Yeah, it works.
Okay, great. So it's an encoder-decoder architecture, and it might sound a little bit weird at the beginning when you see this for the first time, because what you're essentially learning is you're learning the identity function. I give you a space in big D dimensions, and you give me back a space in big D dimensions, so what's the rush, right? The good thing, though, is that you have this other layer in the middle, and this is also sometimes called the bottleneck of the autoencoder or the latent representation. Don't confuse this with the bottleneck distance. These two concepts have nothing to do with each other, but the idea is that you squeeze it through a lower dimensional space to learn some kind of features, some kind of structures in your data that generalize or that are useful for the actual reconstruction. So for instance, you could be learning if you have data living on a manifold and that is parameterized by only two angles, for instance, and you have a very high dimensional point cloud, you could actually be learning some kind of parameterization of these angles, and these are then sufficient to reconstruct the data with high fidelity. And this is why this middle layer is so useful. It's the latent representation that is used for all kinds of things like visualizations, interpolations, clustering, and anything else that you could think about. Classification, of course, as well. I forgot about that one, because if you have a very simple representation in the middle, you can use that to classify things. The simplest autoencoder, and then I'm going to stop there, it is really the simplest one that you can build, is you take a linear transformation from D dimensions to 2 dimensions. The decoder is taking this thing and scaling it in the other way, and as your loss function, you pick a mean squared error. So you're literally just checking whether you get more or less like the same point cloud, the same input data out that you put in. And this loss function is also one of the cool things that you have in this type of space, in this type of architecture, because you can change it. Let me show you how this looks in practice. So this is a simple autoencoder that I trained on digit reconstructions, and the reconstructions don't really get that great if I run them for like 50 epochs, but you can sort of see that at some point it learns how to reconstruct digits, and this is with a very simple autoencoder. So now, of course, this is ancient. I'm not putting this as state of the art here. I'm putting it as an illustrative example here. There's tons of architectures out there, variational autoencoders, for instance, convolutional autoencoders. All of those use different types of techniques, different types of architectures, but the core is still the same. You have some kind of loss that you need to minimize. Now, this is exactly where our topological autoencoders framework comes into play. We circumvent this. We ignore the reconstruction loss. Well, no, we don't ignore it so much. We augment it by a topological loss. So instead of just looking at the reconstruction in terms of geometrical terms, mean squared error, whatever, we go to the space of persistence diagrams, both in the input data and the latent data, or the latent code here, and we calculate a topological loss based on the persistence diagrams. How do we do this? Well, we do this based on differentiable representations of these Rieck complexes. And this is where I want to give you brief intuition. You can find a much more detailed description in the works of Poulenard, for instance, and the works of Carrière that I mentioned before. But here, let me give you an intuition of why this might work. So to calculate the Rieck complex, we only need a distance matrix. That's one of the cool things I would say. So we don't really care about coordinates, making this a very generalizable representation. If we now map this matrix into the persistence diagram, we can see that under mild conditions, namely all the distances are unique, we can get a unique mapping from one point of the diagram back to one distance in the matrix, or actually looks a little bit weird because it's two distances, but it's a distance matrix, so it's symmetric, so it's really the same distance all over again. So takeaway is that every point can be mapped to one distance, and moreover, as you change this matrix a little bit, the diagram changes continuously as a function of the matrix. Unless you change it too much, then you lose this kind of guarantee. But this means that technically we can always backpropagate a gradient through that, so we can always change our input distances according to persistence diagram that we get out. Yeah.
That's H0.
Yes. Yeah, that's true. Yeah. For H1, it gets a little bit more complicated. We need to think a little bit about what feature gives rise to a simplex. So we have to know a little bit about the filtration, and we have to say which coordinates give rise to the feature. But in general, this whole idea, I would say, generalizes to high dimensions as well. Now, this gives us a way to calculate this loss term, and maybe you now feel a little bit misled because I talked about distances before and bottleneck distances and Wasserstein distances. I want to stress that this is not a distance here, but we'll get to that later on. So this is just a simple loss term that we developed for this type of approach. It's bidirectional, so the first thing measures uses the persistence pairing of the input data, so pi of x, and kind of checks how well this is aligned with the persistence pairing of the latent representation and vice versa. So we get a loss term that measures how well we preserve topological features when going from the input data to the latent representation, and then a loss term that tells us how well we do it when we go from the latent representation back to the input data. So this works out very well, and you can see we were kind of inspired by having a, let's say, like a mean squared error here, so we wanted to use this type of Euclidean distance here. I do want to stress that this is just a similarity measure, so it is possible that you have a distance of 0 here without having exactly the same input data. But it was chosen because it works well, and it can be easily optimized over in practice. With this, there we go. I was wondering why this took so long. Yeah, it takes so long because there's a lot of points to show here. So with this, we can plug this into a vanilla autoencoder architecture, or just autoencoder as we call this here, and we can see some qualitative results. This is a data set that we constructed specifically to showcase some of the properties of topological loss terms. It consists of a big sphere, and inside the sphere you have smaller spheres that are nested. So the idea was that even if we just focus on H0, we should be able to reconstruct some of these nesting relationships, and we should make it possible for the autoencoder to pick up that not everything can be split up easily here. And you can see that existing techniques like PCA or UMAP or TSNE or whatever, they all distort this type of representation to a certain extent. So you can still see the other spheres in UMAP and in TSNE as well, but you can't see this big sphere that contains them. This is also not possible with the autoencoder, so the regular autoencoder just pulls everything apart and tells you, okay, here are some pieces that you can put together, fair enough. But with a topologically constrained autoencoder, you can get this to work, and you can see that also the differences in magnitude, so to speak, are represented here because we have a big sphere and it contains some smaller spheres. So it's kind of nice, qualitatively okay, very nice for visualization. We can also zoom a little bit in, and we can see what happens here. So you can really see that this just nudges the original autoencoder in a little bit of a different direction to give you some kind of additional representation.
What does the original data set look like?
It's a 100-dimensional sphere that comprises 10 different lower dimensional spheres.
Okay.
And we put those so that they are nested. And of course, I want to stress that this is a super ill-constrained problem in some sense, because of course we're going from very high dimension space to very low dimension to just 2 dimensions. But this was done on purpose because we found that many people use these autoencoders actually to visualize their data, so to use this as some kind of more fancy way of visualizing data nowadays. And we thought that it would be prudent to be aware of the errors that happen during these types of visualizations as they are being done in machine learning. So, for some reason this is repeated, but that's not a problem. But let's look at a quantitative evaluation metric also briefly. So we use a distance to measure density estimator from Chesal's work, for instance, and we essentially just check whether we can match the density of our input data to the density of the reconstruction. And yeah, I don't want to bore you too much with these numbers, but what you can see here is that this topological autoencoder is actually very, very good in preserving the density. It also fares quite well in other dimensionality reduction measures. Whether those other measures are actually good at capturing what is going on in high dimensional spaces is a very interesting debate that we can have either in one of the breaks or after this talk. So I'm happy to fight any one of those measures and even fight my own measure there, because it's really, really tough to say what is actually a good choice here. But bottom line is, it seems to work. It also doesn't massively distort your ordinary errors, so you end up having a somewhat higher reconstruction error because, of course, we force it in a different direction, but the results are still somewhat acceptable. Now, having said all of this about autoencoders and high-dimensional spaces, let me move to a more applied example where we can easily measure the quality and where, moreover, our Wasserstein distances come into play again, and we can have some more nice derivations and differentiable representations. And here, bear with me, this is more or less all I know about biology. Well, okay, I might know a little bit more, but this is all about all I know about this type of data or this type of problem, but it is a very interesting one. So my collaborators use what they call confocal fluorescence microscopy to obtain images of single cells. Again, if you're like me, don't get confused when you read about single cell technology or single cell sequencing technology, because that's unfortunately a very different thing altogether again. So they really mean like taking pictures of an individual cell. So no gene expression going on there, it's just like really a nice picture. And then they're interested in reconstructing the 3D shape of the cell from this microscopy slide. Why do you want to do this? Well, you want to do this because this type of morphological analysis, as they call it, is critical for detecting certain pathologies in the blood. So there's a very nice quote from a paper on red blood cell morphology, which states, when used properly, red blood cell morphology can be a key tool for laboratory hematology professionals to recommend appropriate clinical and laboratory follow-up and to select the best tests for definitive diagnosis. And at the risk of sounding a little bit like a vampire here, blood is really great because we are really talking not about like a big transfusion or liters of blood, but we're really talking about a small prick and maybe taking some droplets of blood and analyzing them. And you can do this for almost any patient, regardless of their vital signs at the moment, regardless of their stability. So this is one resource that you have readily available in the clinic. And if you can even do this for babies, by the way. Okay, well, now I'm going into monster territory. But what I want to say is that if you have the technology to extract some pathological information from single drops of blood, then this is it is kind of an invasive procedure for sure, because you take some fluids, but it is as non-invasive as invasive procedures go. So this is why I want to stress why I am personally excited about this. Now I also have to open like a little bit of a bracket that I have to open, unfortunately. So there used to be this company called Theranos, which claimed that they could do similar things. We're not even close at claiming these things. But I think the general principle that those people, even though they defrauded their investors heavily, the general principle that they wanted to have was still kind of a good idea. So making rapid blood analysis available to the general public. So yeah, but we're not asking for funding here, so you can hopefully believe my results a little bit. Okay, now with all of that being said, let me show you what we came up with, or rather what Dominic, one of my collaborators, came up with from the beginning. So he developed a method called Shaper, which is the shape reconstructing autoencoder. And the full pipeline works a little bit like this. We're going to discuss some of the intricate parts now. You take a 2D input, so single slice, use a magical machine learning model, which I'm going to show you in a second. You do a 3D prediction from that, and you take a 3D ground truth, so people have actually done these reconstructions, and you measure geometrical loss term. We're going to see examples of how this works. Now, what we did in the paper that I showcased below, we added this additional component here, where we also take topological features from both of these, and we add a topological loss term. It's similar in scope or in spirit to the autoencoders, where we also say, okay, the geometry-based loss is not enough because we need the topology-based loss to steer the calculations. I also want to stress that mathematically speaking, this is complicated to do because it's a complicated inverse problem, because we go from 2D to 3D. So of course, things are bound to be incorrect. It's still defined. There's a number of potential solutions, which is why we need to train a lot of images, and which is also why we need some kind of prior information about what is going on. Now, the architecture of this autoencoder is pretty cool. It has some kind of convolutional layers in the beginning, and then the rest is just like scaling up layers based on fully connected neural networks. So as neural network architectures go, this is a pretty standard one, I would say, and pretty easy still to implement. We have code available for this. It works pretty well, even on a normal CPU. I tried this out. I can even run it on my laptop. It's pretty nice. What we formally learn, because that's, I think, of interest to us mathematicians here, we learn a kind of likelihood function from a three-dimensional grid to, well, a likelihood space. So this likelihood function tells us how likely it is that a specific voxel, so a specific 3D pixel, is part of the actual shape that we want to predict or not. So we don't learn any color information or whatever here, but we really just learn this likelihood function. And this is the original geometry-based loss. It uses a combination of a dice loss and the binary cross entropy loss. Where essentially the binary cross entropy checks how well the likelihood functions are kind of aligned, and the dice loss just checks how well the volumes are aligned. However, the problem with these losses is that they do this on a per voxel calculation. So essentially, if you shift your volume a little bit, or if you turn it a little bit, then you end up getting very, very bad errors, even though you're reconstructing something that is very, very great. And this is also the reason, in my opinion, why the topology-based loss term work very nicely, because when we make this topological and we add a topological component based on the Wasserstein distance between the persistence diagrams and a total persistence regularization term, more about that in a second, this worked rather well. And let me show you these two components here. So the first component, the Wasserstein distance, is for aligning the ground truth likelihood function and the predicted function, topologically speaking. And the total persistence term is to reduce the geometrical topological variation of the predicted function, because we can predict shapes that have a very, very weird surface, so that have a lot of oscillations along the surface. But if we have as an additional objective that the total persistence of the predicted function should be as low as possible, then we get rid of these sort of things. Of course, this will never be zero, so I want to make this clear. This loss term will not go to zero, because you always have some kind of topological variation or some kind of total persistence, but it's sufficient for our purposes. And then we can, of course, combine this, and we can just choose a parameter lambda to interpolate between these two losses. And again, without going into too many details here, let me just tell you that with adding this topological loss term, this works in almost all the metrics that we're looking at, and in some cases it has quite substantial benefits for the reconstruction quality of the cells that we can reconstruct with this. And moreover, what I found super funny is that it actually lets the model converge a little bit faster. And I guess that this is the case because having access to this topological information means that you don't spend time exploring weird optimization configurations that differ a little bit. So you already know that, no, this is the wrong way to go. And so yeah, this works. Moreover, this is, I learned recently, and we'll talk about this in the break maybe, but I learned recently that we need to stress these success stories a little bit more in TDA for other people. But what I really also like about this type of project is that the Wasserstein loss term comes at almost no additional computational cost, because it turns out that we can calculate this loss term on a very downsampled type of our volume, so we don't need the full resolution for this volume to see whether we're going in the right direction, and thus it has a negligible impact on the training time, which I think is also great. This, I have to stress, is not a general statement. So in general, we are probably better off using the type of data that we have and the full resolution that we have. But for this specific application, it wonderfully worked out, and I'm happy about this. Okay, this brings me to the end here. So I hopefully was able to convince you a little bit that topology can provide some nice, what we call inductive biases or prior information, if you will, for these type of shape reconstruction tasks. I also want to stress that what I find very exciting here is that we now have also some empirical proof, again, that persistence diagrams encode geometrical and topological properties of the data because they really help in these tasks. And moreover, and this I think is very nice to stress from the application point of view, the integration into your standard machine learning models appears to be possible now. So we have one application where we use this for a point cloud thing. We have one application where we use this with a cubical complex thing where we work directly on the volume, and both work nicely. So there weren't any real obstacles to overcome except for maybe the computational scalability. And of course, there's a bunch of publications that might be interesting here. So the first is just a survey where we try to talk a little bit about what things are going on in the topological machine learning world. And the second and third one are the respective papers that I talked about in this talk here. I also want to stress that if you're interested in trying out these things for yourself, there's a software that we're currently developing in my lab, PyTorch Topological. Happy to have more contributors there and make this work. It's supposed to be a software package that makes it easy for you to try out whether topological things work. It's not supposed to be super fast, so it's really more about having some kind of convenient starting point for your experiments, and I hope that this can be helpful in this space. Yeah, and yeah, thanks for your attention, and thanks to my collaborators, of course.
Any question?
Yeah, so that was super interesting. I was just wondering, with the morphology thing, have you tried stuff like the K-Turner's work on
Yeah, fully agree. So just to repeat it for the online audience, because I'm not sure where they heard this, so whether we tried the persistent homology transform for the morphology data, the answer is not yet, but we're planning to, because indeed this could be very useful to do. It seemed more convenient at the beginning for us to just do this in a kind of cubical complex persistent homology extraction type of pipeline, but I think the next step would be this, and I actually have a master's student that is very interested in working on this, so I hope that this will come soon. But thank you.
Could this be used inside a K-mapper algorithm to use as a projection?
Okay, the question is whether this can be used in a K-mapper algorithm as a type of projection. Honestly, I don't know the method, the K-mapper method well enough to really say this. So if I can generalize this from the normal mapper representation, then maybe this could be used as some kind of lens function or filtering function. But I have to state that we haven't investigated this. So maybe we should just discuss this in more detail.
Okay, thanks. And how fast is to converge?
The conversion speed of the last method is about, I think, a small data set of about 500 or 600 images takes a few minutes to be fully trained. So with all with different epochs and some hyperparameter tuning, and these minutes are measured on my CPU implementation. So it's not even, there's no GPU involved. In total, I think we can run the full pipeline on one GPU in about 1 hour. So with all the hyperparameter tuning and stuff like this. So it's really reasonably fast, I would say.
Okay, thank you.
Another one?
Yeah, so just I've always found that this is not a mathematical question, but I always find interesting. Like, did you work with biologists on in particular the last one, the capturing the shape? And if so, what did the biologists think of this? Like, do they trust it? Are they skeptical? Like, what's their reaction to it? If people actually would use it?
Yeah. So the question is about the reaction of the biologists. So the data set that we have been working on this was collected before I joined Helmholtz. So I had no say in this or no discussion there. I know that the biologists that we're working with, they are very open to these approaches, and they are kind of happy to see the progression of the reconstruction quality that we're showing them. That being said, this is not close to really big rollout yet, because for this we would need more data sets, and also more data sets potentially from different domains or from different microscopes to see whether the representations we're learning actually generalize. But what I really can stress is that our collaborators are very, very happy and very, very open to try these approaches, because for them it's a little bit like, and maybe it's bad for me to say this on the record while being recorded, but they have so many great technologies for producing these data sets and for generating these insights and these images, but then they lack the toolbox to actually derive some kind of generalizable insights on a large scale basis from these data sets. So they're really, I don't want to say desperate, but I would rather say they're really, really open towards trying out new technologies. And in particular, I think the whole TDA approach in biology is almost becoming an accepted standard nowadays, because when we give them the 60-second elevator pitch summary and say, hey, this is a method for looking at the shape of your data, then they say, sure, okay, great, bring it on. Our data has shape and we want to understand this. So this is also one of the reasons why, closing the loop here, maybe a little bit why I'm so excited about biomedical applications and biological applications, because they do have these massively cool data sets, and they're really, really happy for any type of insights that one can generate from this. And moreover, maybe that's answering a different question now, but I just wanted to mention this. One of the great things that TDA can do in this space is that it's not, I mean, this is coupled with machine learning now, but even without the machine learning thing, you can derive quite a lot of interesting insights here, because you don't have the usual problem that that standard deep learning applications would have, where they would say, give us 1 million labeled images and we'll give you something back. We don't need this necessarily. Of course, we will benefit from having more labeled data available, in particular when you throw a big neural network at the end, but TDA can work well on its own here, and we can at least say, if you have 100 examples, we can at least tell you something about their distribution, and no neural network can do this at the moment, or at least no untrained one, maybe pre-trained ones, but I'm a little bit hazy there, and that's opening a whole other can of worms, sorry.
Yeah, so did you test it, like what kind of artifacts you add, and that gives you, the better results?
Yes. So the question is about the artifacts that we had when we used this reconstruction. So one thing that we found is that without the topological constraints, we end up getting kind of bubbles that are being enclosed by the volume. So unfortunately, I don't have those on the slides here, but I can maybe show you some cool 3D models where you can zoom in and you can see that that the normal neural network, it almost learns like a plane that has some kind of bubbles in it if you don't tell it that this should not be happening. So it kind of invents new artifacts, or at least given the random initialization of the weights, it starts with some very, very distorted or almost degenerate version of a volume, and then it takes a long time to turn this into something nice. So.
No, but I was also thinking, like, what kind of tricks you can do to actually, even with this topological addition, you get this wrong.
Yeah.
Like, what are the limits?
Yeah. The limits. Yeah. So I think one of the limits that we still face is that we are not really good at capturing curved surfaces quite well, because I mean, we know that topologically speaking, it really doesn't matter a lot for us. We just find essentially the void, right, and then that's it. So there are some complicated cell geometries that look a little bit like a torus. No, not like a torus, like a blown up disk, and with some indentations on the side, or a little bit like one of these cough drop pills that you sometimes see. And those indentations, getting those right is still problematic. So this R method also doesn't manage at the moment so well.
Any more question? No?
Are the slides going to be available? Slides will be available?
Yeah.
Site.
The slides will be
yeah.
available.
The site, yeah.
Yeah, definitely. They just send us around.
Possibly also the entire video recording, but at least the slides. Yeah. So thank you, Bastian.
Thank you very much.